Okay, video number 4 in the How to Wire Schneider Modicon expansion modules. We're going to take a look at wiring AC outputs on a relay type of expansion module. Specifically, we're going to be looking at this model over here, the TM3, that's the family, DQ, that stands for discrete, and Q is going to be output. 8, which tells us the number of outputs we have. R tells us that it's going to be relay type. So that's the one that we're going to feature in this video that we're going to draw our connections to. However, if you were looking at the larger one, the DQ16R over here, it's going to be the exact same concepts that we are going to use, just expanded out with a few more commons and input terminals. So you can use what you've learned inside of here on those as well. Let's take a look at what the data sheet says on them. The first thing the data sheet does tell us is the range of families we can use it with: 222, 241, 251, and 261. So across pretty much the entire family over there. It is a normally open relay style. We can use as positive or negative logic, and then the output voltage that we can switch through there is no more than 24 volts if it's going to be DC. This is because DC has a much harder time to go and interrupt the arcs compared with AC, which crosses the zero axis 120 times a second here in North America, or 100 times a second in Europe, right? 50 hertz, 60 hertz. So we can go to either 240 volts AC or 24 volts DC that we could go and put through it. The amount of current that we can go and travel through it is going to be 2,000 milliamps. It's a little bit funny to see it written as 2,000 milliamps. Really, you could just write that out as being 2 amps as being the maximum current that you could put through that one. Other than that, the rest of the information is more minutia. There's a few of them that are kind of interesting. This one here tells us the mechanical durability here is going to be 20 million cycles, or 20 megacycles that you would go and have for this. The amount of time to go and turn on, 10 milliseconds to turn on, 5 milliseconds for this thing to go and turn off. And then this down here tells us that the maximum cable distance between devices that this thing is going to be able to control is going no more than 30 meters, that they would like you to keep it under. All right, let's move on then to our data sheet. Our data sheet for this one is the TM3DQ8R, and what it shows is it shows us 2 options. We're going to have basically option A and option B over here. We're going to go and ignore option B for now. We're going to deal with some stuff from option B later on, but we're going to take a look at option A. Oops, sorry, I just went one too far there. We're going to take a look at option A with this one, because option A gives us 2 types of voltage that we're going to go and have over here, and shows that we can go and take, this first set, Q0 through Q3, and we could either apply AC through it, or we could go and apply DC through it. What it is not showing is that we're simultaneously applying AC and DC. That would be a failure. You're going to have an arc show, it's not going to go well. So we're going to ignore this because we're dealing with AC over here. We're going to go with this one over here. And specifically, we picked this one because this would be what we consider to be a sourcing output. If you don't know sourcing and sinking, take a look at video 2 in the M221 series. Go through and find out what that is. But a sourcing output basically means we're going to go and take our live line. We're going to take that from this AC supply here. We're going to take a hot line through a fuse holder over here, and then into the common, and then it goes through the inside of the common, and it distributes out to the rest of these. And that's going to mean that we're going to then have a hot coming out of our PLC, going through a fuse once again, and then hitting our field device. And then on the other side of the field device, we've got the neutral. We'll just use that light blue for the neutral. This would be a sourcing output. This is the way that you should do it if you have the opportunity, because almost every system worldwide, not just here in Canada, but United States, UK, all over the place, the neutrals are going to be grounded. And so if we would have a fault, this is going to be your safer one, a sourcing output. Okay, let's go and take a look at the fuse holders that we'll use for that. Then we'll move on to the actual connection. The fuse holders that we commonly use are going to be DIN rail mounted, either these or these. This one over here is designed for CC fuses. Use it with the fast acting HCLR style. Or this one over here, which is designed for the small glass or ceramic fuses that you can go and have. Both of these do have indicator lights on them that will, notify you when you have got a blown fuse off of them. Okay, next thing that we're going to take a look at here is going to be this transient suppressor, and I actually didn't identify that for you on one of the earlier drawings, but if you take a look at this drawing over here, what they show over here is that there's a little device being placed in parallel with my load, and if my load is going to be a relay coil, we want to put a transient suppressor that's going to be next to it that's going to be able to take any inductive kick. And this just really means that our relays themselves will last much, much longer. So going to this over here, this is exactly what that transient suppressor is going to go and look like. It's an LA4 or LAD4, the style that we are going to have. You'll note that it's got two little tabs up here that allow it to connect directly onto the coil itself. It's good for 110 to 250 volts AC, and we're going to be using 110, so we'll stick with this one over here. To put one of these onto your device, you've got a contactor over here. All you're going to do is you're going to go and insert it into the side here. It makes direct connection to the coil, clicks in, doesn't take up any additional space on your DIN rail. Okay, now let's go and connect our devices. So the first thing that we are going to do is we are going to go and choose the way that we are going to distribute our power. If you take a look, we're using once again that TM221CE16R, which has got AC coming in. We distribute that AC through that DIN rail breaker. We take it through a fuse holder. This powers up this PLC, and what we see as well is that we've also taken it just a step further over to this fuse holder over here. I don't have fuse holders for my individual outputs off of here. It would be better if we did have them for that. However, otherwise the drawing just gets too crowded, so we're simplifying it. But you should be using plenty of fuse holders, one per output as well as one for the common that we're going to bring in. Let's start with this common. We will take this from here. So we're going to go and run from here. We're going to run to one of my commons. Now we could run it to both commons, or we could run it just to a single individual common one at a time. We'll do this one over here. We're taking power in. That means that now we're going to be able to go from here and take power out to my load. So we'll take it out to this first contactor over here. We'll take one from this out, and we will run that thing around to my A1 terminal off of here. Next thing that we would have to do would be go from my A2 terminal, it's a 120 volt coil, and we could run that back down to my neutral over here. And at this point, you should be able to track through a complete path for power coming from your AC in, power through the fuse holder, coming into the PLC, going through the card, running back through the coil inside of here to energize that, hitting the neutral, and finding your way back through. So we've got a complete path, so we know it's a good one that we have over there. Let's do this other one over here. This other one is also going to need a neutral. Now this one has got the addition of this block on the bottom. For those of you that recognize it, this is going to be an overload block, which is basically going to be a current sensing block that's going to monitor the load that I'm running through there, and it will trip anytime that we pull too much current through. We've got a set of normally closed contacts down here right on the bottom. We'll just zoom in right there. You can see them 95, 96 normally closed. We've also got another set that are going to be normally open, 97, 98 over there. We're going to use these normally closed ones in line with my power that I'm going to bring in. Some people will take it through the neutral, others will take it through the line. We're going to take ours through the line just because there's rule 28500 in our Canadian Electrical Code that talks about when we can run our neutral through a safety device. If it's inside of the same cabinet, it's 100% allowable. If, however, this contactor was mounted remotely from the relay pad cabinet, even if it was just one cabinet away, you would not be allowed. So it's safer just to keep your neutral onto your A2 and then do things the way that we are going to inside of here. And that's going to be that we're going to take an output from here. So take from that one there. We are going to run that output down. We are going to go and take it into a normally closed connection inside of there. And then out of that normally closed, we then flow up to our coil over here. And at this point, we would have a complete path for current. It travels through. There's a set of normally closed contacts that's going to be inside of there. Following it through here, as far as power flow goes, what we see is that we come through our DIN rail breaker. We then distribute out to my DIN rail fuse holder. We go through my DIN rail fuse holder. We can then travel through the card and carry my power through the normally closed up to my coil. At that point, it will energize the coil, and from there we can go and hop all the way back along the neutral. And that's going to be our complete current path for one of these as an AC output. The only difference between the two contactors that we're really looking at is just the fact that this second one over here does have that overload block that's going to be attached to it. If you're unfamiliar with the way that a contactor and overload block work, look up through my channel. There's a whole other video on how to go and utilize them.